Hello, everybody. Welcome back. So in the last few weeks, we talked about how to implement so-called context-sensitive interprocedural analysis, and we have already taken a look at the call strings approach, and I explained the functional approach in general, and we also talked about the Vasco framework, and this week I actually want to talk about another conceptual framework that is called IFDS, which stands for Interprocedural Finite Distributive Subset Problems. It's a complex term, so you can imagine why we have that acronym. To motivate this again, let me briefly recap this example that we discussed. So I had shown you this example of a constant propagation in Vasco. And if you remember, there was this procedure here that took two parameters, h and I. But the second parameter, I, it was not actually relevant for the procedure summary because this parameter, well, is printed, but it's never returned in any way. So with respect to the summary, it doesn't really matter. But these two call sites here, in fact, they had different valuations for I. So at the one call site, it was 2, and at the other call site, it was 3. And this caused the problem that now, if you look at the whole input environment here, that actually differs for the different call sites. And this then triggers a complete re-evaluation of this function actually for the entire procedure, which can be rather expensive. And I want to discuss today an approach that can solve that problem, at least to a certain extent. And that I want to talk about today. And in order to get there, I want to briefly recap what I discussed before about distributivity, because that is actually going to be an important property today. So if you recap, I had presented you this idea that if we have flow functions that can be decomposed this way, right, where a flow function is composed of individual microfunctions that map to this output value D2 here from all the given input values individually. That's the important point, that they do it individually, and where the result can then be obtained through a meet. If you have this setup, then we said that you can actually use that to come up with such a summary approach here that summarizes the concatenation of these two functions through such a representation here. And we also said that this is equivalent whenever this equation here holds, right? And that's exactly the case when you have distributivity of these individual flow functions over this meet or merge operator. And for this lecture today, this is exactly something that we want to assume. So for Vasco, we said Vasco is very general. It can be applied to any data flow analysis problem that fits into the monotone framework. There are no additional requirements. But for the data flow problems that we are going to look into today, we assume that they are distributive. So for all the flow functions defined in the problem, this equation here holds. And there's a very nice framework, IFDS, which was invented by Thomas Reps, Susan Horwitz, and Moody Sagev in the 90s. And that was published in this paper that you can see here. I encourage you all to take a look. It's not the most simple read, but hopefully after this lecture today, you will understand the paper a bit better. The term IFDS stands for the following. It really defines a number of constraints that we assume on this problem to make it fit into the framework. So first of all, the problem that we define, it has to be a subset problem. So that means in our terms, if you have two different data flow elements coming from the left-hand side and right-hand side of a branch, and they are being merged together, then the merge operator is this time a fixed merge operator is defined to be set union. So in IFDS, set union is the only merge operator that you can compute. If you need to compute another merge operator, then you cannot use the IFDS framework as it is. Also, like I said, the problem has to be distributive, and we already talked about this. Here I've just simply rephrased the equation, basically saying that we have not just any merge operator, but we have set union. And then it holds that it doesn't really matter whether you first apply the union operator and then apply a flow function, or you do it the other way around. You're guaranteed to get the same result. If this is true, then you can apply the IFDS framework. And this is what you see here. You have an interprocedural problem, but it's distributive and it's a subset problem. And it also has to be finite. That is something that we will be discussing at the end of today's lecture and also more extensively next week. Because if you have an infinite domain, then the IFDS framework also won't really work. You will essentially get non-termination. But nonetheless, although you might think that these restrictions that I just talked about might be very restrictive indeed, nonetheless, there are actually a number of applications out there that are real-world applications and that nonetheless fit into this framework. So in particular, taint analysis is the prototypical problem that you can fit into IFDS, but also type state analysis works and even some forms of alias and shape analysis, as I will also discuss in my follow-up course DECA 2. And what's really nice about IFDS is that it has a very simple, at least once you have understood it, a very simple underlying idea, which is that it reduces the interprocedural analysis problem, a context-sensitive interprocedural analysis problem, to a pure graph reachability problem. And graph reachability, we know how to solve, right? I mean, it's just graph traversal. That's pretty simple, and that also makes it very efficiently solvable. The question is, though, how do you do this reduction? How do you reduce an analysis problem over a very specific program that you want to analyze to a graph reachability problem? And in essence, IFDS does this by specializing the interprocedural control flow graph of the program that you're analyzing to the analysis that you are conducting. So you take the control flow graph and you sort of do a cross product with a special representation of your flow functions. And that's really the trick here. It's a graph-based representation of these flow functions that allows you to do that. And then what you get out of this is what's in the IFDS paper called a so-called exploded supergraph. So it's a programmed supergraph, an ICFG, but it's exploded in the sense that where normally you have a single ICFG node because it's a single program statement, this time you can have multiple nodes that actually represent a number of different data flow facts. And once you have this exploded supergraph, then you have this nice correspondence here. So a given data flow fact F that you may want to compute, it holds at a given statement S if one of these exploded supergraph nodes, S, F, is actually reachable in the graph, right? So we have a node that corresponds to the fact F at the statement S, and it's an exploded supergraph node, therefore it's such a pair. And if that is reachable at all in the graph, then you know that this fact holds. Now the question is, how in practice do we transform the analysis problem to this graph reachability problem? And I wish to explain that to you by example on the next few slides. Let's assume, first of all, we want to represent the most simple flow function you can probably think of. It's the identity function, right? So it's the function that doesn't change anything, that maps everything onto itself. And in particular, we want to represent this here. So we want to say that every fact is reachable after the statement that is annotated with its identity function, if and only if it was previously reachable, okay? And now we use such a graph-based representation. So if we assume that F and G and H are data flow facts that can potentially be in the inset of the current statement, which is represented through these exploded supergraph nodes here, then these nodes down here, they represent our outset. So the facts that should be reachable after the statement. And now you can think about how we would represent an identity function. I guess hopefully it's very simple for you. It's simply such a mapping here, right? So you have these edges that map every fact onto itself. And what's important now is that you can see this as a conditional generation of a data flow fact. So this data flow fact after the statement is generated if and only if the same data flow fact was already valid before the statement. Okay, that's the condition. So an edge basically defines a condition, but because everything here is conditionalized simply on itself, in the end, we obtain the identity function. Now let's look at other data flow equations. So we could have a flow function that looks like this. So it's saying, okay, in general, we want to do output whatever was already in the inset. But if f is in the inset, then we also want to generate g, and else we simply keep everything as it is, right? And again, you can also think about this in terms of reachability. So we say every fact is reachable if and only if it was previously reachable already, but g is also reachable if f was reachable before. Now, how do we represent this? It's basically, again, the identity function, but now with an additional edge. We now have this edge that is generating the fact g also when f was reachable earlier, right? And this is actually a sufficient condition, right? So you could have a data flow environment, for instance, that at which f holds and h holds, but g does not hold in the input. Then nonetheless, g will be generated, so it will be in the outset, right? Now we can extend this, right? We can also say in the else branch here, we want to kill g, right? So in the other case where f is not in the inset, we want to kill g, we want to take it out of the set. And killing is simply done by not putting an edge here, right? So this data flow function representation here, it would generate g if f is valid earlier, just as before. But in all the other cases, and in particular, also if g is not valid, or no, actually independently of whether g is valid or not, g will be killed, right? So in other terms, the only way now to make g hold in the outset is to have f hold earlier, okay? And in general, like I said, killing is done by not putting an edge. So you could also kill everything in the outset by simply not putting any edge at all. Now, if you take a look at this particular flow function here, you might think, okay, Professor Bodden, he's thinking of these interesting flow functions, but when is that ever sensible, right? When would I write a flow function that looks like this? But you can think about this for a second, maybe. So here we have a situation where such a value g, which might represent a variable, for instance, right? It's assigned something that's coming from a variable, or well, from a node, but let's assume that's a variable f, right? And at the same time, we're killing whatever we already knew about g. We've seen something like that before. Essentially, that would be a data flow equation for a taint analysis, and in particular for a taint analysis for such an assignment, right? So if we have an assignment from f to g, then we want to say that g is tainted if and only if f was previously tainted, right? And really if and only if, right? So it doesn't matter, g could even have been tainted earlier. If it's overwritten with an untainted value, then also g becomes untainted, right? So we really want to kill the old value of g, but we want to propagate the value of f. And so what's nice here is that you really see this one-to-one correspondence, right? So really taintedness, so whether or not a value is tainted at a given statement, exactly corresponds to whether or not the respective node is reachable in the graph. And like I said, you can kill values by not putting an edge. We already saw this. But then you can also generate values out of thin air. And that's also important. For instance, if we have a source statement, as we already discussed in taint analysis, but can also be useful in many other kinds of analysis, there you also need to generate such information. So whenever basically you want to generate information that holds irrespective of anything else, right? So no matter what was true previously in the program, I know that after the statement, if secret is a taint source, then F is definitely going to be tainted, okay? So that means in terms of the data flow equation, we have something like this. It doesn't matter what's in the inset, we definitely add F to it to obtain the outset, right? And if that is the case, then in IFDS, we model this through such a special fact, which is represented by a zero node. So that's just a special placeholder node. And the zero fact is also called the tautological fact. So that is a fact that is always reachable by definition. So even if F was unreachable before, right? So if it was unreachable here, by drawing an edge from this always reachable fact 0 to F, we now make F reachable no matter what, right? So basically the framework assures that you always have an edge from 0 to 0. That's always the case. And in fact, many IFDS implementations, they would not really implement it that way because implicitly it's always there, right? So you don't really need to store it in memory, but conceptually, you know that it's always there, so 0 is always reachable, and by drawing such an edge, you therefore also make the target value unconditionally reachable as well. So that's very nice, right? So we can take all these nice functions and we can represent them through such a summary. You can even represent some complex functions like I showed you. And now we can even think about such a function as here, which looks as follows. So let's take a look at this function. So it's basically saying I want to add h to the outset under a certain condition. And that condition is if f and g are both in the input set. Okay. And now you can think about how that could be represented through such edges. And if you think about that for a minute, then you will figure out that it's sort of problematic, right? Because I could draw an edge from F to H and from G to H, but that would give me a different semantics. That would tell me that H should be part of the outset if either F or G are part of the inset. And they don't necessarily both have to be part of the inset, right? And so here I want to really check the entire subset. And it turns out that this cannot be represented by IFDS because you would need sort of such a hyper edge, right? That sort of looks at both input values at the same time. And it turns out that when you have such a situation that you depend on precise information about multiple input values, then you leave the realm of distributive analysis problems, at least in general. So you get something that is not distributive anymore, and that cannot be represented by IFDS, therefore. And one such problem, for instance, that you have seen already in the previous lectures is full constant propagation. So in full constant propagation, we sometimes have the situation that we have an equation such as A equals B plus C. And then in order to determine a precise value for A, we must also know the precise value for B and C, right? And so that's a non-distributive problem. That does not fit the framework like I showed you here. So much about the conceptual idea behind IFDS. After a short break, I want to go through this example with you where we will really show how to piece this together, how to build an entire exploded supergraph for this example, based on these individual subgraphs that I've explained so far.